Let's dive right into this explainer and explore the totally awe-inspiring engineering behind the world's most extensive high-speed rail network. Whether you're a massive transit geek or you're just fascinated by mega infrastructure, the sheer scale and the technological leaps we're looking at today are absolutely staggering. We're going to break down exactly how this network evolved from its early blueprints to setting global standards, and we'll do it all entirely through the data. Okay, so you might have seen this famous internet trick. A passenger stands a coin on its edge right on the windowsill of a train that is just rocketing across the countryside, and it doesn't even wobble. Now, the answer here isn't magic, it is mind-blowing engineering. Seriously, how do you move thousands of tons of metal at 350 kilometers per hour while keeping the ride so unbelievably smooth that a coin stays perfectly balanced? Well, it all starts with the foundation.
Section 1. High-Speed Evolution, a Rapid Ascent.
To really understand where this tech is going, we got to look at how fast it ascended. The journey kicked off with early milestones like the Qinshen passenger dedicated line. But the true acceleration really began with the 2004 Railway Network Plan. Engineers climbed this technological ladder incredibly fast. This started out with technology introduction, basically importing early tech to meet immediate capacity needs. Then, by 2008, they transitioned into absorption innovation, where they heavily modified those designs to handle local environments. And finally, all of this culminated in complete, independent innovation. They literally took the training wheels off and started building entirely new platforms completely from scratch. Section 2. Anatomy of Folksing, the CR400BF masterpiece. When you are pushing past 300 kilometers per hour, the air itself basically turns into a solid brick wall. So compared to the older Hexi class, engineers actually extended the Fuxing CR400BF's head by roughly 2 meters, giving it this much sleeker, elongated profile. Slicing through the air like that drops aerodynamic drag by a massive 12%. And that is a huge deal. It's not just about going faster, that 12% saves an enormous amount of energy. Section 3. Buggies and control, speed and stability. Now, if you aren't familiar with transit engineering, you might be wondering, what on earth is a bogie? Think of it as the incredibly complex suspension and wheel assembly that keeps the massive train glued to the tracks. It's the absolute critical mechanical component that supports the vehicle body, handles the traction and braking, and, most importantly for that coin trick, it buffers the immense vibrations that get generated at those ultra-high speeds. These heavy-duty turning frames have been through incredibly rigorous testing on specialized test benches and circular tracks. And here's the coolest part, they are meticulously designed with a 500 kilometer per hour redundancy threshold. That means the hardware is over-engineered to safely handle extreme operational speeds way beyond their daily 350 kilometer per hour runs. They literally do it without breaking a sweat, ensuring just absolute reliability. But mechanical perfection just isn't enough on its own. These physical turning frames are coupled with the CTS3 digital control system. Think of it like a massive, invisible automated safety net. It strictly monitors and perfectly synchronizes every single train on the grid in real time. It's flawlessly managing the flow of these high-speed projectiles across thousands of kilometers of track. Section 4. The seatbelt paradox, safety in design. So having all these massive trains rocketing around brings up a really fascinating paradox. Why are there absolutely zero seatbelts at 350 kilometers per hour? I mean, think about it. Your car requires a seatbelt at just 100 kilometers an hour, and airplanes make you buckle up for a 250 kilometer per hour takeoff. Why would a train going over 3 times that speed just completely skip them? It seems totally backward, right? While the physics of comfort here are actually super unique. First off, that unmatched track and bogie stability we talked about completely eliminates the turbulence or sharp turns you'd feel in a car or a plane. But second, it all comes down to crash dynamics. A train operates on a fixed axis, it isn't going to spin or roll. In the highly unlikely event of rapid deceleration, the deeply cushioned seats are actually designed to absorb the impact. Being rigidly strapped in by a tight belt could actually cause severe localized injuries, so the environment itself is engineered to be your restraint. Section 5. The CR450 Future, Pushing Boundaries. And engineers certainly aren't stopping at 350. The upcoming CR450 project is pushing boundaries even further, targeting an eventual design speed of 450 kilometers per hour. To pull this off, it features a 15-meter needle-like head to just completely conquer air resistance, carbon fiber equipment cabins, and a special suspension floor to block out vibrations. They've even lowered the chassis by 20 centimeters so it practically hugs the rails, dropping cabin noise by another 2 to 4 decibels. But honestly, here is the most astonishing number of the whole project. By utilizing these advanced composite materials and entirely rethinking the internal structure, engineers managed to shave a staggering 50 tons off the train's total weight. That's a 10% reduction in mass. Less mass means it requires significantly less energy to accelerate all that metal. So this massive weight reduction, combined with unparalleled aerodynamics and that lowered chassis, will safely push everyday operational speeds to a jaw-dropping 400 kilometers per hour by the time the design is finalized in 2026. And what's really incredible here is that it will achieve this 400 kilometer per hour speed using roughly the exact same amount of energy as current models use to go just 350. It's wild to think we've gone from importing early technology to designing ultra-lightweight carbon fiber trains that will casually cruise at 400 kilometers an hour. As we look at these monumental leaps in engineering and this relentless pursuit of efficiency, I want to leave you with this one thought. With constant innovations in aerodynamics, materials, and digital control, just how fast will the future allow us to go on the ground before we literally take flight? Thanks so much for joining me on this explainer, and keep your eyes on the tracks ahead.